All right, integration, finding the area underneath curves. Here, example 13.3, estimate the area underneath the function the square root of x from x is equal to 0 to x is equal to 4 using a right-hand Riemann sum using 4 rectangles. So it says sketch this Riemann sum. You do this for every Riemann sum that you do, right? Every approximation to an integral using rectangles, it's a good idea to draw the function and see what's going on. Let's zoom in here so I can give some detail to it. It's the square root function. I know its domain is only positive numbers, so let's only graph that section. And also, I'm only concerned between 0 and 4. So let's put 1 there, 2 there, 3 there, and 4 there. The square root function does something like this. All right, now I want to estimate the area underneath this from 0 to 4. And I'm going to use rectangles to do this. So it specifies that I need to use a right-hand Riemann sum. You can use a left hand if you want to. Really, any Riemann sum is going to give you a decent approximation, or rather an approximation. So let's figure out how wide each rectangle needs to be. I'm going to take my interval and divide it by how many rectangles I need to squeeze in that interval. My interval is between 0 and 4, right? It has a distance of 4. And how many rectangles do I want to squeeze in? 4 of them. So each rectangle needs to have a width of 1. So I start here, I go over to 1, and I want to construct a right-hand Riemann sum. So this rectangle, I'm going to raise it up until the right-hand point is my function. The function at the right-hand point of that interval gives me my rectangle, or rather the height of my rectangle. All right, the next rectangle has a width of 1. So we're going to go from 1 to 2. And again, we're using a right-hand Riemann sum. So I take the right point and I use that function value for the height of my rectangle. Our third rectangle has a width of 1. It's a right-hand Riemann sum. And then finally, our fourth rectangle completes the interval and is another right-hand sum. Okay. So the area between 0 and 4 of the function f of x is approximately equal to the sum of the areas of these rectangles. All right, you can see that it's not a perfect approximation, and it's going to be an over approximation because of all this extra area that we're getting. But it's not a bad idea, it's not a bad picture. So what is the sum of all those areas of rectangles? It's the sum of a bunch of bases times heights, right? Because the area of a rectangle is base times height. The first rectangle, what's the area of that guy right there? It's a base of 1, and the height is given to me by my function value at 1. So a base of 1 times my function value at 1. I'm then going to add to it the next area. The area of that rectangle has a base of 1, and the height of that rectangle is the function value at 2. My third rectangle has a base of 1 and a height of f of 3. My fourth rectangle has a base of 1 and a height of f of 4. So base of 1, height of the function at 3, base of 1, height of the function at 4. Okay, well, everything's being multiplied by 1. 1 is the multiplicative identity. It doesn't change anything. I just need to sum f of 1, f of 2, f of 3, and f of 4. So remember, this is the square root function, right? This function that gives you your y values is the square root. So what is the square root of 1? What is the square root of 2, square root of 3, and square root of 4? Now, this is the perfect answer, or rather, it's the exact answer to the approximation. If you wanted to stick this into a calculator, obviously square root of 1 is 1. But if you wanted to add all of this together, you get something about 6.147. So there's about 6.147 square units of space here. Actually, I shouldn't have done that because the square units are there. But there's about 6.1 square units.